Hi everyone. In the last video we learned about the different entropies of continuous channels, and also we learned about the different entropies and information rate of different waveform channels including Gaussian channels. Okay, so now just like in the discrete source, when we learned about the entropies, the next thing we learned was the mutual information. Likewise over here also, in the case of a continuous channel also, what we are going to learn is the mutual information. Okay, so we already know what is mutual information. Mutual information is the information that is actually mutual, or that is being known to both the transmitter and the receiver. That is the information that is being passed through the channel. That's what we call as the mutual information, right? So we know that the entropy definition of continuous channel is the relative measure, and using logarithmic property we can now define the entropy relations. So these are the different entropy relations, and the reason of why it is called as a relative measure we all know, because each of these entropies are called as differential entropies. They are not the actual entropies, they are not the absolute entropies, they are differential. These entropies are called as differential entropies. Okay, so as usual, the name, now since we all know, we can now define each and every equations of entropies, right? Since there are, how many entropies are there? There are 5 entropies, so we can define each of these 5 entropies. That is h of x. If you want to know h of x, that's simply right, h of x is equal to integral minus infinity to plus infinity f of x log of 1 by f of x dx. Likewise, h of y is equal to integral from minus infinity to plus infinity f of y log of 1 by f of y dy. Here x stands for the transmitter, y stands for the receiver or the received signal. H of xy is called as the joint entropy. So joint entropy is equal to integral from minus infinity to plus infinity minus again integral from minus infinity to plus infinity f of xy log of 1 by f of xy dx dy. This is a double integration. Okay, likewise this is a conditional entropy, h of x by y. And look at the equation of h of x by y, integral from minus infinity to plus infinity, again integral from minus infinity to plus infinity, f of xy log of 1 by f of x by y. This is exactly the same as your conditional entropy of discrete channel, right? In the discrete channel, what would be the equation? That is sigma k is equal to 1 to m, sigma j is equal to 1 to n, p of xk yj log of 1 by p of xk by yj. That is this is the probability density function of this same probability density function, and likewise over here only is the only difference between these two equations, right? Dx dy. Likewise same case over here also, in the h of y by x also same procedure. This is exactly the same. These 3 terms will be exactly the same, only these 3 terms will be different. So h of y by x is equal to double integration from minus infinity to plus infinity f of xy log of 1 by f of y by x dx dy. Okay, so now we know now we can understand the correlations between different entropies. We can now understand the relations between entropies and how to write the equations also. Okay, now next we are going to learn is the equation for the mutual information, and the equations for mutual information is exactly the same as your discrete channel that you have studied before. That is, the mutual information of a continuous channel is given by same equations. I of xy is equal to h of x minus h of x by y, or I of xy can also be used as h of y minus h of y by x, or you can also define mutual information as h of x plus h of y minus h of xy. You see the same equations that you have used earlier in your first when you were learning about the discrete channels. The same equation for the mutual information. Okay, so if you are now able to tell what is mutual information, then it is now very easy for you to say what is channel capacity. And channel capacity is nothing but C is equal to the maximum value of mutual information. Channel capacity is the same equation, everything is same, just like how you studied in the previous discrete sources, right? There also you learned about channel capacity, and there also this equation is the same. That is, channel capacity is equal to maximum value of mutual information. Maximum value of mutual information means, if you want, channel capacity C is equal to maximum value of this equation, or the maximum value of this equation, or the maximum value of this equation. If it's a maximum value of this equation, it is called as h of x max minus h of x by y max. If it is a maximum value of this equation, then channel capacity is equal to h of y max minus h of y by x max. Or if you want, channel capacity of this equation is h of x max plus h of y max minus h of x by h of xy max, where h of x max, h of y max, h of xy max are all the maximum values of the entropies. Okay, so this equation you can use. This equation you can use if you want to define the channel capacity in bits per sample unit. If you want the channel capacity in the units of bits per sample, then the equation for channel capacity is this equation. The maximum value of the mutual information, or the maximum value of this, any of these three equations. That is the equation for the channel capacity. Now, this one thing you already learned, just like how you have studied before. If you want to define the channel capacity C in terms of bits per second, if you want the unit of channel capacity in terms of bits per second, if you want the channel capacity in terms of bits per second, then just like how you have studied before, the equation for channel capacity C will become R of x max minus R of x by y max, or R of y max minus R of y by x max, or R of x max plus R of y max minus R of xy max. So we all know what is R of x max and R of y max, and what is R of x and R of y? Those are the information rate. Those are the information rate. That is, R of x is equal to nothing but the R, small letter r into h of x, where small letter r is the sample rate, the sample rate of the signal. So if you want, you can either define the channel capacity in terms of bits per sample, or channel capacity in terms of bits per second. If it is bits per second, it will be, everything will be in terms of R of x or R of y, like that it goes, R of x, R of y, where R of x and R of y are nothing but the channel rate, information rate. Okay, so that is something you understand about the channel capacity. Now, and mutual information. Now, one more thing also you need to understand about the mutual information is this statement. That is, mutual information is time invariant under all linear transformations at the input and at the output of the channel. This means that that is one of the beautiful property of this mutual information. That is, if you apply any linear changes to the input and to the output, identical linear changes both to the input and to the output, if you make any changes to the input and the output, the mutual information will not change. That is, the mutual information still remains the same. That is what this statement is saying. That is, mutual information is time invariant. Time invariant means does not change with time. That is the meaning of this property. So I'm going to prove this equation right now. Okay, I'm going to prove this equation. So in order to prove this equation, let us start. I'm going to say that let x and y, okay, let capital letter X and capital letter Y be the input and output continuous random variables. Okay, X and Y are the input and output continuous random variables. Okay, and also I can also say, in that case I can also say let small letter x and small letter y be their sample values, respectively. That is, small letter x is the sample value of capital letter X, and small letter y is the sample value of capital letter Y. Okay, so in that case, then their entropies are defined as, let's start with h of x. So what is the equation for h of x? I can say that h of x is equal to integral from minus infinity to plus infinity f of x log of 1 by f of x dx, where f of x is the probability density function of the input signal x. Okay, so this is one equation, and same way I can now say the equation for h of y, entropy of the received signal, is now can be defined as integral from minus infinity to plus infinity f of y log of 1 by f of y dy. Okay, just like how you say that f of x is the probability density function of x, the same way f of y is the probability density function of the received signal y. Okay, and also the joint entropy also. Okay, the joint entropy also I am going to define it using the equation h of x comma y is equal to double integration, one for dx, another one is for dy, minus infinity to plus infinity, minus infinity to plus infinity f of x comma y log of 1 by f of x comma y dx dy. Okay, the reason why I'm defining these three entropies is because my mutual information, the equation for mutual information, therefore the mutual information is given by I of xy is equal to h of x plus h of y minus h of x comma y. This is the equation I'm going to use for this proof. I'm going to use the third equation. Okay, that's why I defined these three entropies. Okay, so now what I'm going to do is I'm going to change my input signal and my output signal. Here the input signal is x and the output signal is y. So now what I'm going to do is I'm going to change the input signal and the output signal. That is, now let x1 and y1 be the new input and output signals. So in that case, how I'm going to change is that the input signal x1 is equal to ax1 plus b. You see, I have multiplied my ax, not ax, it is not ax1, it is ax. Okay, my old input signal. Okay, so how I'm going to change my signal is that I'm going to multiply my input signal with a and then I'm going to add with an amount of b, so that this is my new signal. So x1 is equal to ax plus b, and y1 is equal to cy plus d. Okay, this is my new received signal. So this is my new transmitted signal, this is my new received signal. Okay, so now what I'm going to do, so according to this statement, even if the input signal and the output signal are being transformed, if they are now linearly transformed, then even then also the value of the mutual information remains the same. That is, it still remains as I of xy itself. That is what this statement is saying. So that is what I'm going to prove now. So therefore, now I know what is the input signal, my new input signal equation, and this is my new output signal. So now what I'm going to do is I'm going to find the mutual information of this signal. Okay, I'm going to find the mutual information of this signal. So to find the mutual information, what I'm going to do is, since we already know that the random variables are having this equation, then their sample values are also having the same equation, right? That is, if x1, let x1 and x2 be the sample values. I'm going to write that also. That is, let small letter x1 and small letter y1 be their corresponding sample values. Okay, in that case then I can also say that small letter x1, okay, x1 is equal to, just like this, a into small letter x plus b, where x1 is the sample value of x1 and small letter x is the sample value of capital letter X. Okay, in the same way over here also, y1 is equal to ay plus d, cy plus d. Okay, so now what I'm going to do is I'm going to differentiate these two equations. Okay, that is, I'm going to differentiate this equation with respect to x, and I'm going to differentiate this equation with respect to y. So if I differentiate this with respect to x, what do I get? Therefore, dx1 by dx is equal to a, and over here also dy1 by dy, I'm going to differentiate with respect to y, is equal to c. Okay, or in other words, dx1 is equal to a dx and dy1 is equal to c dy. Okay, I'm going to use this equation. This equation is used in my coming equations. That is y. Okay, so now, one more thing also. So now I know I have written the differential equations of these two equations. So now what I'm going to do is I'm going to find the relation between the probability density function. That is, here, look over here, f of x is the probability density function of this signal, f of y is the probability density function of this signal, and f of xy is the joint probability density function of this entropy of xy signals, right? So what I'm going to do is, now I'm going to find my probability density function of f of x1, f of y1 and f of x1 y1 over here. So in that case, what's my probability density function is, we know that according to fundamental theorem, comma, that is f of x1 dx1 is equal to f of x dx, and f of y1 dy1 is equal to f of y dy. Okay, that is, we all know that the probability density function is the probability per unit area into the small area dx. So this represents the probability. So even if you apply linear transformations to both the input and the output signals, the probability of each of these, the probability of these individual sample values remains the same. That is what this means over here. That is, the probability still remains the same. That is why f of x dx1 is equal to f of x dx and f of y1 dy1 is equal to f of y dy. Okay, so in that case, I can now say that f of x, or f of x1 dx1 by dx is equal to f of x, right? So we all know what is dx1 by dx, which is nothing but a. Or I can say that f of x1 is equal to f of x by a, right? Similarly, f of y1 is equal to f of y by c. Just like this over here, right? How you would, if you want, you can I can show it to you right now. That is, we all know that dy1 is equal to c dy, right? So f of y1 c dy is equal to f of y dy. So therefore dy will cancel, so f of y1 is equal to f of y by c, just like this. Okay, so now I know the probability density function of x1 and probability density function of y1. Okay, so now if I know the probability density function, now I can write the differential entropies of x1 and y1, right? So therefore the entropies of x1 and y1 are defined as h of x1 is equal to integral from minus infinity to plus infinity. Instead of f of x, we have f of x1 log of 1 by f of x1 dx1. Okay, this is the equation for h of x1. So but now we know what is f of x1, right? F of x1 is f of x by a. So I'm going to substitute the value of f of x1 as f of x by a, and also I know the value of dx1. What is dx1? Dx1 is a dx. So I will substitute that also over here. So in the other case, so in other words, h of x1 is equal to integral from minus infinity to plus infinity. It becomes f of x by a log of a by f of x into, and dx1 is a into dx. Okay, so what I'm going to do is I'm going to this numerator a and denominator a will get cancel each other. So I will get this equation as integral from minus infinity to plus infinity f of x log of a by f of x dx. Okay, so now I can split this log. I can split this function into two terms. Okay, that is, we know that log ab is equal to log a plus log b. So in that case, I'm going to split this like this. That is, this can be written as integral from minus infinity to plus infinity f of x. Now this is nothing but log 1 by f of x plus log a. Okay, dx. Okay, so in that case, now I'm going to put this integral f of x dx inside the bracket. So this will become integral from minus infinity to plus infinity f of x log of 1 by f of x dx plus, and over here log a is a constant, right? So I can write like this, that is log a into integral from minus infinity to plus infinity f of x dx. Okay, now we already know what is integral from minus infinity to plus infinity f of x log of 1 by f of x dx, right? We already know what is that. What is that? It is nothing but our h of x itself. So in that case, this equation is nothing but h of x. This is nothing but h of x and plus, and what is log a into, what is integral f of x dx? That is what happens, like I said before, if you add all the probabilities, you will get 1. In that case, in the same way, if you integrate all the area and the probability density function, the value will be unity. So this is nothing but h of x plus log a. So therefore, I have now found out that h of x1 is equal to h of x plus log a. Okay, So now I want you all, the same way, I want you all to prove, okay, as a homework, as a part of this, derivation, okay. I'm just going to write the answer, but I want you all to do it as a homework, okay. That is, similarly, I can also prove that h of y1 is equal to h of y plus log c. The same way, exactly the same method and all exactly the same, okay. Everything is exactly the same. So like that, I can also prove that h of y1 is equal to h of y plus log c, okay. And also add h of xy, h of x1 y1, sorry, h of x1 y1, that is a joint entropy of x1 y1, okay. I can also prove that this equation, maybe this equation, if you want, I'll just show it to you right now, okay. But this I want you all, as a part of the continuation of this derivation, I want you also to prove this statement by yourself, okay, and then followed by this remaining equations. So I'll just prove to you how this is going to come. That is h of x1 y1. This is also equal to integral from minus infinity to plus infinity, integral from minus infinity to plus infinity, f of x1 y1 log of 1 by f of x1 y1 dx1 dy1, okay. So here there is dx1 dy1. So what is of f of x of, what is the relation between f of x1 y1 with f of xy? Let's see about that. In that case also same thing, okay. According to the fundamental theorem, I can say that f of x1 y1 is equal to, or f of x1 y1 dx1 dy1, f of x1 y1 dx1 dy1 is equal to f of xy into d of x d of y, just like how you wrote the fundamental theorem of this function, that is f of x1 dx1 is equal to f of x dx, and f of y1 dy1 is equal to f of y dy. I can also prove that f of x1 y1 dx1 dy1 is equal to f of xy dx dy, okay. So in that case, what I'm going to do is, just like over here also, okay, just like over here, if I'm going to write this equation in this term, then in that case I can say that f of x1 y1 dx1 by dx, that is this dx I brought over here, into dy1 by dy, that is this dy I brought over here, is equal to f of x y, okay. So like I said before, what is dx1 by dx? Just like how I did over here, dx1 by dx is a and dy1 by dy is c. So therefore these two are nothing but f of x1 comma y1 into a into c is equal to f of x comma y, okay. Or in other words, f of x1 y1 is equal to, which is what I need, f of x1 y1 is equal to f of xy by ac. So now I found this equation. Now I will substitute this equation over here. So that case, h of x1 y1 is equal to integral from minus infinity to plus infinity, again integral from minus infinity to plus infinity. So f of x1 y1 is nothing but f of x y by ac log of 1 by f of x1 y1 is ac by f of x comma y, okay. Put a comma also here, okay. And also here we know that dx1 is a dx and dy1 is a c dy. So in that case, this is nothing but a dx into c dy, okay. And this a will cancel each other. this c and this c will cancel each other. So therefore I can now say that h of x1 y1 is equal to integral from minus infinity to plus infinity, again integral from minus infinity to plus infinity, f of xy or f of x comma y log of a c by f of x y dx dy. Okay, and just like that, just like here, now the procedure is exactly the same like over here. Okay, exactly the same, no change. That is, this can also be written as integral from minus infinity to plus infinity, integral from minus infinity to plus infinity, f of x comma y into log of, or I'm going to split this, so log of 1 by f of x comma y plus log ac dx dy. I'm going to put this inside the bracket, so this will now become integral from minus infinity to plus infinity, integral from minus infinity to plus infinity, f of x comma y log of 1 by f of x comma y dx dy plus, now over here this log ac is a constant, so I can take it outside, right? So this will become plus log ac integral from minus infinity to plus infinity, integral from minus infinity to plus infinity, f of x comma y dx dy. Okay, and this is equal to, this whole thing is nothing but h of x comma y plus, and this thing from integral from minus infinity to plus infinity, integral from minus infinity to plus infinity, f of xy dx dy is nothing but, this value is nothing but, this is again the area under the whole area under the probability density function, which is equal to unity. So therefore this is into 1, so this is log ac into 1 is log ac itself, so this is log ac. Okay, so now, so what did I find? I found that h of x1 is equal to h of x plus log a. I also found that h of y1 is h of y plus log c, and I also found that h of xy, h of x1 y1 is equal to h of x1 y1 is equal to h of xy plus log ac. Okay, I found out that. Now what I'm going to do is I'm going to find the equation for mutual information, that is the mutual information of x1 comma y1 is given by I of x1 comma y1. Okay, I of x1 comma y1 is equal to, we all know the equation, right? So just like how we write the equation, we know that I of xy is equal to h of x plus h of y minus h of xy. The same way, I of x1 y1 is equal to h of x1 plus h of y1 minus h of x1 comma y1. Okay, this is the equation for mutual information. So what is the equation for h of x1? The equation for h of x1 we already know, it is nothing but h of x plus log a. So therefore this is nothing but h of x plus log a. Plus, we all know what is the equation for h of y1. That is, you need to prove this. Okay, as a part of this, I want you all to do this by yourself. Okay, so anyway, over here, h of y1 is h of y1 is equal to h of y plus log c. So this is nothing but h of y plus log c minus, and h of x1 y1 is h of xy plus log ac, right? So therefore this is minus h of x comma y minus log AC. Okay. Now I'm going to rearrange these terms. That is, this is nothing but h of x plus h of y minus h of x comma y plus log a plus log c minus log AC. We all know what is h of x plus h of y minus h of xy, right? What is h of x plus h of y minus h of xy? It is nothing but the mutual information of the old input and output signals, I of xy. So therefore this entire thing is nothing but I of xy. So therefore this is equal to I of x comma y plus, and I'm going to combine all these log functions into a single log function. That is, this is we know that log AB is equal to log A plus log B. We also know that log A by B is equal to log A minus log B. So I'm going to use that property over here. So therefore this is nothing but log of, if I were to combine all this will become log of A into C by AC, right? So this is actually plus log of A into C by AC. Therefore this is nothing but log 1, and log 1 is nothing but 0. So therefore I can say that I of x1 comma y1, I of x1 comma y1 is equal to I of xy plus log 1, which log 1 is 0. So therefore I of x1 y1 is equal to I of xy, which means your mutual information is the same. That is, even the mutual information of the new signals is equal to the mutual information of the old signal, which means even if you apply any linear changes to both the input or the output signal, the mutual information will not change. The mutual information remains the same. Okay. That is what this equation means. Therefore, mutual information is time invariant or does not change with time under all linear transformations of the input and output signals. Okay, this is the proof. This is one of the important property of the mutual information. Okay.